This is our video on seismic waves, or S and P waves, that you need to know for the AQA specification. So what you've got to learn today is the structure of the non-observable parts of the Earth we're going to quickly look at, and then link S and P waves and how we use them to explain the structure of the Earth. At the end we'll just do some very straightforward calculations so you can see how they would or how they can be used. So first up, just some background. Is the highest mountain higher than the deepest ocean is deep? How high do the mountains go and how deep do the oceans go? So obviously you probably know about Everest, and then we've got something called the Mariana Trench. But in terms of the numbers, well, we can see here the Mariana Trench is about 6.8 miles or 11 kilometers deep, and the Everest is about 8.8 kilometers deep. So in terms of the deepest or the greatest distance, well, the oceans are deeper than the mountains are high. So we probably don't know a lot about the bottom of the oceans. Some people say we know very little about the bottom of the oceans. In some ways we know more about the moon, I think I've heard. So we've got the limits of our exploration is about 11-12 kilometers. So how do we know anything about the structure of the Earth if we've only got to this depth? Because you must have seen pictures and you've probably heard about the internal structure of the Earth. And really, how do we know this is the big question to ask. So here's the structure of the Earth. If we go from 6 downwards, so we'll go from the surface. The Earth's crust is about 70 kilometres thick, something called the lithosphere. The next level is 250 kilometres. Then we've got the upper mantle, the lower mantle, the outer core and the inner core. Now you don't need to know these, but in order to understand the significance of S and P waves, I think you do need to have an appreciation that we have got different layers to the Earth, and these different layers are going to have different densities. Okay, so here's a more kind of detail. The core is very hot metal, mostly iron and nickel. The mantle is mostly solid rock, but some parts are slushy, like lava. And the crust is very thin, it's solid, and it's almost like the shell of an egg in terms of its thickness. Okay. And remember, throughout this lesson so far, we've only explored a tiny way into the crust, about 12 kilometres. So how do we know all of this? Okay, so here we go. Here's the main part. Seismic waves are two types, and these are the shock waves that travel through the Earth. And there are primary waves, which are longitudinal waves. These are called push and pull waves, so they're linked with P for primary. They're very quick, 30 times faster than sound. They can travel in solids and liquids, but they do travel much faster in solids. So primary waves are longitudinal. Secondary waves are transverse waves, and these are more side to side, and the S can help you to learn it. They're much slower than P waves, and they can only travel in solids. And this difference that S waves can only travel in solids and P waves can travel in both has led to an increase in our understanding. This little images might help you understand more what we mean by P waves. You can see P waves at the top. It's like a longitudinal wave, whereas the S wave is like a transverse. And you've got the side-to-side motion on the transverse and the backwards and forwards motion on the P wave, the longitudinal. Okay, so let's apply this. Here's some P waves. As the P waves go through the structure of the Earth, P and S waves are both refracted because the Earth will get denser as you go down. So both of the types of waves are refracted as they travel through the different layers. But notice there is a shadow zone where no S waves get through. And this, if you remember, S waves can't get through liquid. So there would be a shadow zone if the centre of the Earth was indeed liquid or molten. Okay, and what happens is by comparing the differences in the waves, seismograph stations over the Earth in many different places can compare P and S waves produced in earthquakes and can do some calculations on the size of the Earth's core and also that it's liquid. So it's not guesswork, it is by looking at P waves and S waves from earthquakes and by looking at them at different points on the Earth's surface. Okay, so just to finish, a really straightforward calculation. You can see I've got quite a complicated picture of some P and S waves. If we had an earthquake occurs at an unknown distance from seismic station D, so here's seismic station D, the average speed of P waves is 10 kilometers per second and S waves are 6 kilometers per second. If the time taken by the P waves was 900 seconds, how far away did the earthquake occur? Well, let's just use simple distance of earthquake is distance equals speed times time. We know that they're 900 seconds and they go at 10 kilometers per second. So it's 9,000 kilometers. The next question, how long later did the S waves arrive? Well, the time lag for an S wave, if we work out the time it's going to take for the S wave, we've just calculated the distance, 9,000, divided by the speed, 6 kilometers per second, gives us a time of 1,500 seconds. But this isn't the answer, remember, because the difference in time is going to be 1,500 minus the time for the P waves, which was 900 were given in the question. So 1,500 minus 900 will give us 600 seconds, which is of course 10 minutes. So you can see at that point there would have been a time lag from the one earthquake. The two different waves would have taken different amounts of time. And from calculations such as these, obviously much more complicated, the earth structure was worked out over the years.